Alright, so next up in our review sessions, we're going to go with Electrostatics. Now in class we kind of combined a lot of electricity and magnetism together kind of as one monolithic thing. Although if you pay close attention and as you watch when we go through each of these, you'll see that they were actually smaller pieces. The first is called electrostatics, where electro for charged particles, things like electrons, and statics. If you remember back from when we talked about statics, that dealt with things that were sitting still. So this is where we began originally, things with Coulomb's law and a few other relationships where we talked about fields and voltages, potentials, all of that. We're going to review that here. Pardon me, that deals with electrostatics. The next part that we looked at were electric circuits, and then the final part we looked at was electromagnetism, where we brought magnetism back into this. So, let's get started. Now, I'm going to start off with fundamentally the most important equations to remember from electrostatics, and they carry through pretty much all of electricity and magnetism for both of the AP classes, for pretty much all of physics in general. I'm not going with the Maxwell's equations, but I am going with something very, very important, and that is these. These are universally true. Force equals our electric field times our charge. And our potential energy equals our potential, our voltage, times our charge. These are universally the case. If you're dealing with the AP or any of the questions I give you or anything like that, if you can use these relationships, you cannot misuse them. They apply every time, everywhere in the universe, so far as I can recall. For everything you need, these things remain true, and we will see that they will have manifestations. The other things that we'll look at with Coulomb's law, they will still satisfy this. We'll find that the electric field from Coulomb's law, if we multiply that by the charge of the particle itself that's being acted on by the electric field, we'll find the force acting on that particle. By the same token, if we find the potential from point particles and we multiply them by the charge that we're putting at that potential, we find the potential energy that charge has. These are universally true. Keep track of them. Also, very, very important, I'm going to go ahead and mention this conceptual thing here because it's something that we've had problems with and we want to keep track of. Forces and electric fields are both vectors. They have directions. When you add them together, when you're stringing together a bunch of different ones in superposition, where you break the problem, a complex problem, down into its little pieces and add them together, you must add these as vectors. Direction matters. When you're dealing with potential energies and potentials, voltages, direction doesn't matter. Just take the positives and negatives and just run with them. Add them together like you normally would. Okay? When it comes to potential energy, if you're setting it equal to something like kinetic energy and you end up with a negative in there, just drop the negative. Don't worry about it. You're not going to end up with an imaginary velocity. Okay. So, we will come back to that conceptual point because I cannot emphasize it enough. Vector, scalar. Keep track of those. Now let's talk about the more specific ones. Coulomb's law. This is for the force between charged particles. Now normally we're just finding the magnitude of them and we keep track of the direction independently, but if you take a look back at some of the other videos we've had, we've gone through and we've kept track of the direction as well. But Coulomb's law, which I think in class I was marking with F sub c, although that will probably become very confusing with centripetal force. So maybe we should have done it as an E or something like that. However you want to mark it, knock yourself out, but it's Coulomb's law. Okay? That equals K, which is Coulomb's constant, times Q1 times Q2 divided by the distance between them squared. Okay? Now, rightly so, this guy's a vector. Technically, this points in what's called the radial vector. I'm going to put a unit vector in the radial direction. For the most part, if you take a look at a couple of the sample problems, it's pretty easy to keep track of the direction. It's always between these two particles. So if they're attractive, they're towards each other. If it's repulsive, then they push away. On Coulomb's law, when you plug in the charges, if it's negative, if your result comes up as negative, it tells you that it's attractive. And that's also something important because it means that it's pointing in the negative radial direction. You can imagine that as radial direction. Here's my center of the circle. The radius usually points out. If I've got it pointed in instead in the opposite direction, that means that where this guy is, he's being attracted in. So that negative does actually have a mathematical reasoning behind it. When you do end up with a negative here, it just means attractive. Keep track of the vectors, which way they point individually. A quick note for the AP exam, and just more broadly in general, this also carries over to APC a little bit more. Coulomb's constant, K, which is equal to 9 times 10 to the 9th, or 8.99, depending on how precise you want to be. I believe that this is Newton times meter squared per Coulomb squared. This is also equal to 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Again, permittivity of free space describes how easily an electric field flows through, in this case, vacuum or air. Air is close enough to vacuum that we treat them more or less as the same thing. We will see that number come up, or that value come up again for APB specifically in the capacitor equation, and APC uses the capacitor equation too, though they should be prepared to try and derive it. On a related note, so this is our force. Our potential energy under Coulomb's law is going to be K Q1 Q2 over R. No radial direction, no directions of any kind, because potential energy is a scalar. Cannot emphasize that enough. By the same token, I'm not even going to write them down, but if we're finding the electric field from a point particle, well, that's going to be our force. I can divide this by Q. That'd be my force per charge. I'd blot out one of these charges here. I'd only be looking at, say, this guy. I'd ignore the other one. Now, normally, you're finding it around a point where there isn't anything anyway, but you use the charge that is some distance r away. Now, remember, with these r's, it's the distance between the two objects. It's not necessarily, be careful thinking of it as a radius of a circle, because people have a tendency of dividing that by 2, thinking that this value is the diameter. R is the distance between them. By the same token, you can find the potential, the voltage, between 2 points by blotting out the other one here, K, Q over R. Again, same relationship up here. This, if you have command of these, will save you time and trouble memorizing additional things. All right. So, that actually takes care of most of the Coulomb's law related stuff. Couple final things that we're going to take a look at here, because it technically belongs a bit more under electrostatics, though in class I think we doubled back to these after doing a bit with circuits. The capacitance of a parallel plate capacitor, which is kept track of as a C, is epsilon naught, the guy we talked about up there, times the area of those plates divided by the separation distance. And I've got them not far away, so let's grab them, double check that we're familiar with them. These guys, parallel plate capacitors. Area is going to be the area of one of the plates here, so that'll be the area you use. And the separation is how far apart they are, so these are pretty close. This gets further apart. Often you will use these equations, so this is where our capacitors begin. The next equation for capacitors, which is a good one, is Q, the charge on the capacitor, charge, equals V, our voltage across the capacitor, C, our capacitance. If you're dealing with a parallel plate capacitor, this is your capacitance. Okay? So an easy way to remember this is QVC. It's like the home shopping network. They just love charging you for things. Yeah, I'm sorry, you get stuck with terrible jokes. But if you remember it because of that, then more power to you. QVC. Q equals VC. All right, so that's a pretty useful relationship. This relates the charge on a capacitor to the voltage across the capacitor when it's hooked up in a circuit, and, or even when it's disconnected from a circuit, too, as long as it's charged, and the capacitance, the total amount that it can actually hold there. The final thing, and some people were confusing this with the potential energy back up here. The potential energy specifically for a capacitor, this is only for a capacitor, equals 1/2, let me get this right, CV squared, which also equals 1/2 QV by doing a replacement with this guy. Okay? So those are capacitors. We've got one more equation that may or may not make a showing. We have the resistance of a wire is equal to rho, which is called the resistivity. This is a property, it's a bulk property. So if I've got a pile of copper, it's got that as a value. This is usually an ohms times meter is the unit on it. It is going to be times the length. The longer the wire, the more resistance it's going to have, because the current has to go through more and more of it, divided by the cross-sectional area. Cross-sectional area of our wire. Basically, the more room, the thicker the wire, the more the charge can spread out, and it's happier. So it's got a lower resistance. That's a good way of remembering it. Now, cross-sectional area, usually when you're dealing with a wire, you're actually dealing with something that is cylindrical, right? That's usually what we think of with a wire. It continues going this way and this way. And so your cross-sectional area is often going to be pi r squared. Cross-sectional area, in other words, this area on your cylinder. Okay, so this one we kind of blended a lot of the conceptual stuff along with pardon me, the important powerful equations, but I wanted to go through in case people weren't paying close attention to the equations, because especially here there's a big difference. Pay close attention to these. Keep track of vectors and scalars. Know these equations. They're always true. Be familiar with these guys, especially Coulomb's law here, and you should actually be able to piece it together to the potential energies and find your electric fields and your voltages as a result pretty easily with those relationships. Helps to be a little more familiar with the capacitor equations and the resistivity, or the resistance I should say, of a wire. This is the sort of thing that makes for a good conceptual question. It's important to know these relationships, but it's not necessarily the sort of thing that you should kill yourself if you don't know this full equation. Don't worry about it too much, okay? But if you've got the ability to, probably a good investment. Big things, other than vectors versus scalars, which hopefully I have drilled into the ground because it is incredibly important with this sort of thing. Final thing to keep track of is Coulomb's law. I think I usually do this in green. Coulomb's law. And any equation that looks like Coulomb's law, so the ones that have K and Q's over R's, R squareds, whatever, all of the ones that look like Coulomb's law, these are for point particles and spheres only. You can only apply these equations onto point particles and technically onto spheres because they act just like point particles. Okay? That's why, again, I reiterate, these first equations are incredibly powerful because they are always true. They're true for point particles, for spheres, they're true for cylinders, for charges spread all over the place. And that's why these equations are so incredibly important. All right? So I believe that's the majority of the stuff for electrostatics. It's kind of dense, but it turns out that there's a lot of stuff with electricity and magnetism. So we'll see the next one.